Okay, so your ears are great pressure sensors. Your ear can indicate, tell you when you have gone through a change in pressure. Change in pressure is force per area. So inside your ear, there's air, and then there's the eardrum, and then the outside of your ear. So right now, we're all in equilibrium and we all feel good, unless you've got like a crazy head cold or something. Um, but when you go up in an airplane, the air gets thinner. The force applied, or the weight of the air, is different. And so the pressure on the outside of your ear is actually going to go down. But on the inside of your ear, the pressure is the same as it is at sea level or wherever you're used to hanging out. So to equalize that, and you pop your ears, you're just moving around so that the air on the inside and outside can get back in equilibrium. And when you go underwater, a lot of times you can hold your nose and blow. No? Yes, okay. You hold your nose and blow, and you can equalize the pressure that way. So when you're swimming, or when you're, so here we go. Here's our water. We got a fish, and we're going to go swimming here. It's the fluid, or the water that's around you, that makes you your ears feel funny. So let's put him in a scuba diving suit. There we go. So what's on top of your ear? This column of fluid is on top of your ear. And that column of fluid is causing a pressure. And pressure is force per area. So what is the force that's on your ear? The weight of the water. So the force would be mass times the acceleration due to gravity over the area of your ear, or whatever the pressure we're looking at. Now, is water a fluid? Do we measure fluids in mass? Not usually. What do we usually measure them in? Volume. So how do we relate mass and volume? Density. Okay, so if density is mass per volume, then what's mass? Density times volume. So let's make a substitution into our mass right here. Boop. So I'm just going to write it down here below. So pressure would be density times volume times the acceleration due to gravity over area. Now let's look at this volume and area. So instead of it being a column where it looks like a cylinder, what if I was looking at it as being a column that was a rectangular prism? How would you find the volume of this column? And how would you find the area that is pressing down on you? Okay, so let's make some substitutions into our volume and our area in terms of the shape of this object. So density, we'd have length times width. Sorry. Times height times g. Can't leave him out. And area would be what? Length times width? And he's like, I'm not your student. No, get out to me. Okay, so my length and the width can cancel out there. So then what are we left with? That the pressure is rho. H is next and then G, but you won't see the H in front of the G. You'll see it as rho GH. I don't know. H is taller and G can't see over H. I don't know. Something like that. But this is called the gauge pressure. Whoops. Gauge. Gauge pressure. So if you don't say it out loud, say it in your head. Gauge. I get a lot of funny pronunciations for that. So this is the pressure due to the column of fluid. If you're in the water swimming, there are two columns on top of you. One you're just accustomed to having on you all the time because you have it on you right now, and that is what fluid? What fluid are we stuck in all the time? We're stuck in the air. And so you're swimming down here, yay, your little mask on, and you've got this column of water on top of your little ear. But also, what's above the water? Air, that gas. So, you know, if you're hanging out on a raft, let's see if I can make a raft here. Yay, you don't feel, oh, that's some strange feet there. You don't feel any different. Yay, it's feeling good. Because you're accustomed to this atmospheric pressure on you. But if I wanted to find the absolute pressure, I would need to add the pressure of the column of air plus the pressure of the column of water. Now, most of the time, and I'm going to abbreviate this as P-abs, most of the time this air pressure is pretty constant, and we're going to call it P-naught, or the pressure at the beginning. Most of the time, an asterisk, most of the time, this pressure is 1 atm, which is not SI unit. 1 atmosphere of pressure is what you're accustomed to, which is 1.013 times 10 to the 5 Pascal. We have to add in then the pressure of the column of fluid, which may be water, or it may be oil, or it may be coffee, or it may be Jello. I don't care what it is, but rho GH for, which is the gauge pressure. So just as Spencer said, our gauge pressure is the absolute pressure minus the pressure at the top of the column, which is most likely this 1.013 times 10 to the 5 Pascal, or 1 atm. But we can't use 1 atm. It's just easier to say 1 atmosphere than it is to say 1.013 times 10 to the 5 Pascal when you're referring to how you are feeling at one point, or the pressure at sea level. So just another way to look at the same thing. This